They're striking earlier than ever before.
I realized that this was going to be a historic event.
They're getting stronger.
Is there anybody else in there with you? Do you need help? Is there anybody else down here?
And they're striking places they've never been.
If you're living north of Tornado Alley, sometime in the future, tornadoes will start showing up on your doorstep.
Tornadoes are changing. The events of one tragic day will tell us why. A terrifying glimpse of the future that holds the key to saving lives. February 5th, 2008. Super Tuesday. Out across the Central Plains, a storm is brewing. This will be no ordinary storm. As cold, dry weather streams in from the Rockies, unseasonal warm air forces its way north from the Gulf. Where they meet, history will be made. No one expects to see this kind of weather in winter. The first sign of trouble arrives late in the morning. Massive thunderstorms are forming in a line over Texas.
My initial thoughts were I need to get the word out. It's obvious that we are dealing with a major storm system that will produce widespread dangerous weather and that people are at risk.
And by mid-afternoon, the system is beginning to develop the most powerful storms of all. Supercells. One hour later, the situation on the ground goes critical. The start of a trail of death and destruction that sees 87 killer tornadoes drop from the skies over Mississippi, Alabama, Arkansas, Kentucky, and Tennessee, wreaking more than $500 million of damage. "57 people will perish. One of the worst tornado outbreaks ever recorded. But the implications are far worse. Scientists looking at Super Tuesday see a dark future. Stronger, more destructive tornadoes striking outside the traditional tornado season. Striking in places they have rarely been seen before. Tornadoes are changing. So what exactly is happening? The answers lie in the rubble of Super Tuesday. Solving the mystery of this devastating outbreak is a matter of life and death. The investigators start with the biggest mystery of all. How does a tornado form? From here, they can work backwards and figure out what was different about the storms that gave birth to the tornadoes of Super Tuesday. What they know for sure is that tornadoes form in storms like no others. Hurricanes take days to develop, cover thousands of square miles, and follow a discernible path. They begin life in Tornado Alley. stretching from Texas through Oklahoma, right up to Iowa and Nebraska. Vast and flat, and caught in an atmospheric crossfire between north and south, the weather here has all the right ingredients for twisters, and spring is traditionally tornado season. As winter turns to spring, polar air from the Rockies spills across the plains. It sets off on a collision course with warm, moist air heading north from the Gulf of Mexico. The stage is set. Warm air is light and wants to rise. Cool air is heavy and wants to sink. When the two air masses collide, they begin to spin. Tornado expert Robin Tanamachi has a simple way to demonstrate what happens next.
What we have right now is a very unstable arrangement. You can see we've got this very dense, heavy water up in the upper chamber, and the lower chamber is filled with air, which is much less dense than the water. And the air wants to go up into the upper chamber, the water wants to come down.
Scale this instability up a few thousand times, and you get vast thunderclouds called supercells, the birthplace of tornadoes. Compared to regular thunderstorms, they can span 20 miles across and tower twice the height of Mount Everest. Supercells are the most ferocious of all thunderstorms. But the energy in the storm needs an outlet. The cold air wants to sink, and the warm air wants to rise. In order to restore the balance and release the energy, another ingredient needs to be introduced.
You can see some of the air bubbles are kind of traveling up into the upper chamber, but this is a pretty inefficient way to restore the balance to this unbalanced system. And so what I'm going to do is impart a little bit of vorticity to the system by sloshing it around a bit so that now it spins. And now we have a vortex that's formed in the middle, so that now the air is flowing upwards through the center of that vortex into the upper chamber, and the water is flowing downwards into the lower chamber, so that this is a much more efficient way for the system to go back into balance.
The imbalance allows the warm and cold air to mix by spinning them together. It's the fastest way for the heavy air to sink down. This spinning is known as wind shear. This is the second vital ingredient for tornadoes.
So relatively weak winds at the surface, topped by stronger winds aloft, create this roll, and that is shear.
So they know how supercells are created. But why a supercell creates a twister is the last great weather mystery. It seems clues may lie in the spinning motion itself.
Many researchers who've studied them have sometimes called them accidents of nature because it seems so elusive to figure out what actually went together to cause the tornado at the ground. We know how to get a lot of spin in a thunderstorm, but there are definitely some more complex things going on near the ground. We can have spin taking place on small enough scales that we really aren't able to measure it.
Only one supercell in 4 gives birth to a tornado. So what makes that one so special?
We do not know yet what the mysterious missing ingredient is. We think we know what it takes to get a tornado, but there's something mysterious that we still don't understand that determines, sometimes a tornado will touch the ground, sometimes it won't.
But when it does, the results can be devastating. Once the funnel touches down, it starts feeding on an inflow of warm, moist air at ground level. This warm air is called updraft. Low pressure inside the vortex creates a vacuum, and the warm, high-pressure air around it rushes in. Once inside the funnel, the warm air shoots upward, trying to restore the balance, all the time sucking in more and more warm air from the ground. The warm air is the fuel that gives it the energy to move forward. Its funnel sucks up debris as it tracks along the ground. You not only see it coming, you hear it.
Don't go! Jesus Christ!
There have been descriptions of tornadoes that vary from a roar like a freight train, depending on how fast the tornado is moving. If they're inside of a house, they may report that it makes a very high whistling sound, say if it's coming through cracks in windows or something like that.
Yes, a large destructive tornado. There's a large tornado moving through the south side of Atkins.
On Super Tuesday, one of the worst tornadoes ever seen in Arkansas rips through the state, traveling a record 122 miles. Across 7 counties, it leaves 13 people dead. 100 homes in the little town of Atkins are torn apart. But what makes this tornado so unique is that it happens at the wrong time of year. Powerful tornadoes like this very rarely strike in winter, yet Super Tuesday sees 87 of them. Investigators now turn their attention from the tornadoes to the storms that made them. The answers they are about to uncover will bring them one step closer to understanding why tornadoes are going to get worse. On the 5th of February 2008, a devastating tornado outbreak claims 57 lives and leaves experts baffled. 87 powerful tornadoes striking in winter is rare.
Once I sat back and realized it was only the 5th of February, then I realized that this was going to be a historic event.
Freak weather? Or is a pattern emerging? To find out, scientists rework the events leading up to Super Tuesday. One day earlier, and meteorologists at the Storm Prediction Center notice a dangerous wind pattern, one that usually occurs in spring. They are surprised to see warm winds moving north, cool winds heading south. When they meet in Tornado Alley, the chances of tornado formation will be high. Yet tornado season is still 2 months off. Why are these 2 spring air masses meeting in winter? The answer is found in a strange ocean current 1,000 miles away in the Pacific. Joe Schafer, the director of the Storm Prediction Center in Oklahoma, wanted to find out what caused winter tornado outbreaks.
Super Tuesday was in February. To the general public, it probably did come as rather a surprise that you're having this strong activity in February.
He begins by looking for a bigger pattern.
Newest ones are white, the oldest one.
Could the arrival of spring weather in winter be anything to do with La Niña, a vast ocean cooling event in the eastern Pacific? It's a long shot, but he knows it causes extreme weather in the most unlikely places.
There has to be some clues to what Mother Nature is really going to do.
There are always larger patterns at work. The El Niño and La Niña cycle are one of the biggest. The cycle affects vast ocean currents, which govern the warming and cooling of the oceans. The El Niño current drives east, carrying the warm waters of the tropics to the west coast of the Americas. As it does, it warms the atmosphere above it. El Niño lasts about a year. The cycle then reverses and the temperatures drop. This reversal is called La Niña. This current carries cooler seas and cooler air above. The cooler seas of a La Niña year are famous for influencing the increased strength of Atlantic hurricanes. But no one had yet proven a link to tornadoes.
We just looked at the number of tornadoes all across the country and tried to see if there was a relationship between the tornadoes and whether you were in a El Nino, La Nina, which is the opposite, or a neutral pattern, which is neither one. So we looked at those and found absolutely nothing.
Other meteorologists were also searching for a link. But weather systems are some of the most intricate patterns known to science.
People would find one thing, these people would find different conclusions. I more or less had come to the conclusion that there wasn't any link on the thing.
He couldn't believe Super Tuesday was a random event. He was convinced that there was a relationship between events like Super Tuesday and La Niña.
You always have the hope that there's some seed out there of truth, or I never would have looked at it in the first place if I really didn't think someplace in my core that there had to be some kind of relationship.
One day, Joe and his grad student have a brainstorm. Instead of counting each tornado in each year, they look only at outbreaks, days with 6 tornadoes or more. For the years they study, they find twice as many outbreaks occur in a La Niña year than they do in an El Nino year. This doesn't yet explain why the Super Tuesday outbreak occurs in winter. So they refine their search. They begin to focus only on winter tornado outbreaks. They discover that during a La Niña year, winter tornado outbreaks are likely to be more severe. 2008 was a La Niña year. The implications are enormous. Conclusive proof that the winter outbreak on Super Tuesday is caused by the La Niña effect. It's an incredible breakthrough. The mystery of how deadly winter tornado outbreaks can happen is now solved. They realize that La Niña strengthens the cool winds from the northwest, which intensifies wind shear and creates more violent tornadoes. The breakthrough is a milestone in tornado research.
Science is such that if you can actually see the relationship and prove that it exists, then you've made a contribution.
A contribution that may help forecasters save lives in the future. But the mysteries behind the Super Tuesday outbreak are far from solved. We know why it happened in winter, but what scientists now need to find out is why are they so unusually powerful? Forecaster Greg Carbon and his team are the first to spot where the trouble is brewing.
The first watches that were issued across Arkansas were to get the word out that dangerous weather is on the way. Despite the forewarning, despite the watches, and even the tornado warnings that were issued during the event, we still had loss of life.
Nothing can prepare them for the destructive power of the tornadoes they are about to see. Super Tuesday, February 5th, 2008. At 5 p.m., a giant tornado descends on Arkansas. 7 counties lie in its path. The power of this monster is about to take everyone by surprise. Using a system called the Enhanced Fujita Scale, scientists classify the strength of a twister between EF0 and EF5. EF0 can break branches from a tree, and EF2 can lift a roof off. Anything above that is rare. The vortex in an EF5 can reach 300 miles an hour, the fastest known winds on our planet. With wind speeds around 200 miles an hour, the Arkansas tornado is an EF4. And it isn't the only one. Another EF4 tornado touches down in Jackson, Tennessee, 300 miles away. It shreds Union University. Across Tennessee, 1,000 houses destroyed. 32 people killed. Debris is found 70 miles from where it was lifted. Super Tuesday's 5 EF4 twisters reveal an alarming trend. Stronger tornadoes lasting for longer. In a matter of hours, they clocked up more than a quarter of the average annual death toll. To understand why they are so destructive, scientists need to know, where is their energy coming from? Is it also connected to the powerful ocean current during La Niña? If so, how? The first clue lies 30,000 feet above the Great Plains. An invisible force traveling at 300 miles an hour is steering the storms and spinning them faster. A ribbon of wind called the jet stream. It speeds through the highest part of the sky, called the troposphere. The jet stream forms where cool air from the North Pole meets warm air from the equator. As the Earth spins, it sends the air shooting west to east at the point where the two air masses join. As polar air and Gulf air meet, the warm air is sucked up through the thunderstorms and into the troposphere, where it crashes into the jet stream. As the jet stream shoots across the United States and over the tops of the storms, it sucks on these updrafts, spinning up the storm. Just as a gust of wind across a chimney will strengthen a fire, the jet stream strengthens storms. On Super Tuesday, it's winding them up and steering them across the plains.
Here you come, Ryan. I've got the analysis, and it looks like we're starting to see moisture increase across this area and Q coming up. The watches were up. We knew that this potential existed downstream from Arkansas off to the east. It's not that the cells in Arkansas moved directly into parts of Tennessee or across the Mississippi Valley. We now had new development occurring in parts of Mississippi and Tennessee. And that new development quickly acquired supercell characteristics. And the event began to unfold quite rapidly during the evening hours.
By 5:25 that day, the jet stream hurtling across the Midwest was powering up one thundercloud after another. As the monster storms advance on Tornado Alley, some 20 million people are in their sights. When scientists look closer at the events that unfolded on Super Tuesday, they find a compelling piece of evidence that links the strength of the jet stream and the destructive force of the tornadoes to the Pacific Ocean current, La Niña. Because what Dr. Schafer also discovers is that La Niña not only makes winter tornadoes more likely, it also makes them more powerful. During La Niña, cooler temperatures in the eastern Pacific create stronger easterly winds that make the jet stream flow faster. A faster jet stream spawns stronger tornadoes. They spin faster and track on the ground for longer. The result is more destruction. With such high speeds, the debris a powerful tornado carries can turn into missiles. A stalk of straw can fly fast enough to pierce a telephone pole.
Just hit us. It just blew all the glass out and swooped us up in the air, and the next thing I know, we were flipping and flying and landed over here.
Super Tuesday 2008 was one of the worst tornado outbreaks ever. But could tragedy have been prevented? Doug Forsyth at the National Severe Storms Lab in Oklahoma has just set up a new kind of early warning radar station using technology developed by the military. Phased array radar. Traditional radar starts scanning at the bottom of a storm. By the time it gets to the top, the bottom has changed. Too slow to catch every detail of a tornado forming. But phased array radar uses multiple beams that scan in rapid succession.
To improve our lead times, we need to scan faster. With a phased array, if I can do that in less than a minute, then on the second minute, I'm already issuing the warning. So I've already increased my lead time by about four minutes. We're now getting about 13-minute lead time, which is a pretty good lead time, but we'd really like to extend that.
Phased array radar is a 2-for-1 gift. It could be the tool that leads researchers to cracking tornado genesis. And it gives forecasters more time to issue warnings. On Super Tuesday, this could have saved lives. Robin Tanamachi's team now includes a truck with phased array radar. Instead of waiting for storms to hit Doug's radar station, they can go and seek them out.
We in our radar research group feel like we're on the cutting edge using this brand new phased array technology. You get a more detailed picture of the evolution of the storm. You can watch it evolve in much greater detail.
But so far this season, that elusive tornado formation has escaped them. But buried in the data, they have discovered something just as important.
When you get a new data set and you bring it into the computer model and you start studying it, it's kind of like drinking from a fire hose. Your mind just goes off trying to think of all kinds of different things that you can do with this data set and different ways that you can analyze it and visualize it.
After feeding data from a recent storm into the software, Forsyth noticed strange patterns.
We're seeing changes go on in the storm that we've never seen before. There's some waves moving through the storm that I don't think the meteorologists knew existed, because you can't see them when you're taking snapshots between 4 and 6 minutes. You just don't see those things happening.
The brown mass is the storm. The new elements the radar reveals might just be the trigger for the tornadoes, like these waves that seem to ripple through the supercell.
Actually starting to see some new activity in storms that we've never seen before.
If they can detect the waves long enough, before a twister is born, they could gain life-saving minutes.
We're going to have to do some research and see what really is happening. I think we'll put it together over the next few years and make some headway into making better warnings and at least understanding possibly this tornado genesis.
Early warnings will save lives. Buried in the rubble of Super Tuesday lies another life-saving clue. Over 1,000 homes are destroyed on Super Tuesday. Research into new building design shows these losses could be avoided. It has also led to some exciting new insights into what happens within the tornadoes themselves. Investigators combing through the rubble of Super Tuesday discover a frightening truth. Tornadoes are getting more powerful. Is there anything we can do to protect ourselves? The first time wind engineer Partha Sarkar from Iowa State University surveyed the wreckage from a tornado, he was determined to do something about it.
You may survive a tornado, but your entire life is turned upside down because your whole house is gone, whole neighborhood is gone. And that's what bothers me. If you see the cars which have taken a hit from F5, you see it twisted beyond recognition, you know, people are no match for that kind of wind.
On Super Tuesday in Tennessee alone, over 500 homes are destroyed. The cost to rebuild runs into hundreds of millions. Sarkar thinks we can prevent the damage these new, more powerful tornadoes will bring.
We can do something about it. We can design these houses to at least not get completely destroyed. If it's partially destroyed, we can rebuild it. It's completely destroyed and it's gone.
In order to figure out how to protect a building, he has to know exactly what the winds are doing inside a powerful tornado. To do that, he has to make himself one. He contacts tornado expert Bill Gallus.
It was probably a phone call I'll never forget. Partha wanted to design the first wind tunnel that would create a moving tornado and wanted to discuss what ways might we use to create a moving tornado simulator.
This is the result of their collaboration. A twister in a can, 18 feet across and 11 feet high, suspended over a model target. The largest and most realistic tornado simulator ever constructed. It can recreate the same kind of tornadoes that struck on Super Tuesday, from EF4 to the more powerful EF5. It's the only simulator that can accurately measure how the wind loads of a moving tornado affect different kinds of structures.
Once they had the large simulator done and had to throw on the power switch, I think there were a lot of people waiting there and scared to death at what would happen.
In the past, wind tunnel research simulated only straight line wind. This machine reveals how the circular wind of a tornado can literally pull the roof off a house like a corkscrew. New building design will now incorporate ways to prevent this.
Every time I switch on the tornado, I feel good about it.
But this is not the only insight the machine revealed. In order for the simulator to create a tornado, they add a significant amount of downdraft. Could this be one of the elusive ingredients needed to form a real tornado? The team looked closer. Downdraft is a fast current of air passing down through the center of a rotating storm. We don't yet know how downdraft is created, only that it concentrates the storm's rotation by drawing it inward. Downdraft seems to create enough spin to produce a tornado.
It's possible that tornadoes are created in many different ways, but it seems that this particular idea of getting a downdraft that descends toward the ground almost in the shape of a circle should be something that really does lead to tornadoes.
And if tornadoes are getting more powerful, the simulator could tell us more about how they form and what the winds are capable of. But right now, scientists have a more urgent mystery to solve. It seems something else is happening to tornadoes. They're not only getting more powerful, they're not only striking outside tornado season, they're now striking outside Tornado Alley. Forecasters need to understand why. 7:15 p.m. on Super Tuesday, and Arkansas is reeling from 7 tornadoes. Tennessee is now under attack, and more storms are brewing. The team at the Storm Prediction Center can only watch.
There is a feeling of helplessness, really, at that point, because you see the violent weather unfolding. You know that there's most likely a tornado on the ground. You know that there are communities at risk. But you also know you've done just about everything you can do.
As the monster system rampages across the Upper South, it holds one more deadly surprise. Against the odds, one thundercloud crosses the Tennessee state line, moving outside Tornado Alley into Kentucky. On average, Kentucky sees 10 small tornadoes a year, mostly in the spring. It's about to be struck by 24 powerful twisters in a single night. Winter outbreaks usually occur farther south, in Arkansas and Texas, where tornadoes can feed on warmer air. What's causing them to strike so far north? This phenomenally rare event will lead them to the most chilling discovery yet. Super twisters on course for Chicago. The Super Tuesday tornado outbreak has shown that more powerful tornadoes are now striking outside their usual season. The culprit is La Niña. Its cooling effect at sea speeds up the jet stream winds over land, making winter storms spin even faster. The perfect conditions for tornadoes. But there's one last mystery. Why are tornadoes now striking further north, outside of Tornado Alley? Again, the clues lie in the events of that tragic day. 7:35 p.m. Super Tuesday.
We can see the contact point on that one. He's close. There's contact on the ground. There's debris.
Kentucky is about to be terrorized by the first of 24 twisters. A state usually considered too far north to see this many. At the Storm Prediction Center, Greg Carbon can do nothing.
When I went home that evening, I had no idea that there were already 14 fatalities. I knew we had deadly tornadoes. I knew that the day before, but the actual numbers and the actual accounts were yet to be known.
As the Super Tuesday tornadoes trespass into new territory, pushing the death toll higher, the storm too is dying. As a tornado feeds on the warm, moist inflow at ground level, the downdraft that created it keeps descending. As the cold downdraft collects at the base of the tornado, it wraps itself around the vortex and begins to cut off its warm air supply. The tornado is slowly strangled by the very force that gave it life. As the last twister retreats, the Super Tuesday storms finally run out of energy. The imbalance that created them is gone, and equilibrium is restored. But what caused the tornadoes to cross state lines? What gave them the power to move so far north, into places they are least expected? At the Carnegie Institution at Stanford in California, climate scientist Ken Caldeira may have stumbled across the answer. Caldeira is studying the jet stream in the hope of harnessing its power.
If we could somehow tap into this energy, it would be really incredible resource for civilization.
Caldeira set out to develop an atlas showing the best places to launch wind turbines into the jet stream. As he charted the position of the jet stream from year to year, he noticed something alarming. Over the last 2 decades, the jet stream has been shifting north. As it moves, it takes severe storms along with it. This would explain why Kentucky got struck on Super Tuesday.
The jet streams act as storm tracks. They guide storms and also affect where storms are created. And so where tornadoes used to be something that was primarily of the southern areas, now we're seeing tornadoes further and further north.
But what pushes the jet stream north? For the answer, Caldeira looks south. For the last 2 decades, temperatures around the equator have steadily risen. The jet stream is the boundary between tropical air and polar air. As the warm air mass around the equator expands, the polar air mass contracts. As a result, the jet stream is pushed further north. What are the odds that global warming caused Kentucky's freak outbreak?
You could think of weather as a chaotic system, a little bit like rolling dice. In the natural climate, we're rolling the dice, and every once in a while it comes up snake eyes, double ones. And you could think of climate change as loading the dice, where you should expect more snake eyes, more storms like this occurring further to the north as global warming continues. If you're living north of Tornado Alley, but you don't get any tornadoes now, you should be worried that sometime in the future, tornadoes will start showing up on your doorstep.
The jet stream is moving north over 1 mile per year. Before long, Chicago could mark the center of Tornado Alley. Scientists calculate that if a big twister tore through the city of Chicago, it could do $40 billion worth of damage and potentially kill 45,000 people. Understanding what caused the tragic events of Super Tuesday 2008 has enabled science to predict that there is worse to come. The groundbreaking discoveries about La Niña and the jet stream will go down in meteorological history.
The key, I think, for us is to not get frustrated, but to learn from these experiences and to take from them a better understanding in trying to help predict significant events in the future.
One of those significant events could be the ultimate nightmare. A super twister slamming Chicago. But by the time it strikes, we may be ready by cracking the mystery of how tornadoes form, buying enough time to warn victims of danger, and designing buildings to withstand the worst. Science could be the silver lining inside the darkest cloud.